so welcome everyone, and in the previous discussion we have just started the internal forced convection. So let us continue. So I have just introduced you with the internal forced convection, and I have also shown you that in which cases we can neglect the viscous dissipation term, in which cases we can neglect the conduction term, and in which cases we can neglect the pressure work term, right? So now let us focus on our main problem. So today we will start the problem with, so this will be the internal, or I would rather say forced convection inside a pipe with uniform heat flux. Okay, uniform heat flux boundary condition. Okay, so let me quickly draw the geometry, and that is very simple. So these are the walls of the pipe. So what we are doing is that in the real scenario we will have some finite thickness of the walls like this, right? And obviously some of the heat will be conducted through these walls, but as you can see that this length is very large, so that means the conduction resistance is also very large. So we can neglect the conduction, and here our main concern is the solution inside this domain, that is this one. Okay, so let us proceed with that, and we will neglect the thickness of the wall, the effect of the thickness of the wall. And what we will consider is, when we will consider the uniform wall temperature condition, obviously we will consider that the inner and the outer temperature wall, so if this is T1 and this is T2, we will consider that this gap is very small, because you can also see that the conduction resistance is also very small here, because the thickness we will consider very small, thin wall case. Okay, obviously if the wall thickness is considerably large comparable to the channel dimensions, then we have to consider that. Okay, so now this is our geometry. So if I can neglect the wall, or I can uh, put the wall here. So if I put the wall, then my front view will be, so if this is the side view, then my front view will be what? My front view will be something like this, and a smaller circle for the, and for the wall I will have a bigger circle. Okay, okay, so, and this is the center of the channel, so this is the radius r. Okay, and the coordinate system I will consider the r theta. So the r theta coordinate system will be something like this. So this is the small r, and this angle will be theta. Okay, okay, so r theta, and z will be what? This will be the z direction. Okay, so we will consider that the fluid is flowing here, and the inlet condition is uniform. Okay, so uniform velocity profile. Okay, that means mathematically at z equal to okay, so if I consider that my the origin is here, origin O, okay, and this is the z coordinate. At z equal to 0, my velocity is u equal to u bar, the vector, that is equal to u infinity e z cap, okay. This is my velocity. There is no ur component, there is no u theta component. So this is the uniform velocity profile. Now I have already taught you the boundary layer theory in the external force convection. Now you know that at the moment the fluid will be in the contact with the plates, there will be the boundary layer formation, right? So there will be the hydrodynamic boundary layer formation. Now here, unlike the flat plate, we have the confinement and the boundary layers will grow, but in the flat plate we did not have any other confinement, but here we have two boundary layers growing simultaneously. At a point they will meet, okay. Now what is the difference? So you must have studied in this your fluid mechanics when you are studying the Hagen-Pauli flow, okay. So here I will not derive the Hagen-Pauli flow. If I get time, then I will derive in this course only, in some later video, okay. So this is the hydrodynamically developing region, okay, and after that there is some region that is called the field region, okay, and this is the developing region hydrodynamically, and then we have the developed region. So here what will be the velocity profile? The velocity profile will be something like this, that it will at the wall it will be 0, then it will grow, and here it will be the uniform velocity profile, and here again it will be 0, right, okay. Okay, so this is the velocity profile. Now you see that when the fluid is in the contact with the plate, then this is the region in which the viscous effect has been propagated. Therefore the fluid has been slowed down, and because of that, to make the mass flow rate constant, here in the uniform velocity profile the fluid has to accelerate. That means this velocity, that means this value, if it is v1 and if it is v infinity, or I have said here u infinity, okay, so let me call it v infinity. So then v1 must be greater than v infinity. So here the flow will accelerate, right, to have the same mass flow rate, and that means the center line velocity, and that is the maximum velocity inside the pipe in the developing region, that must increase, right. And that means here at any section, if I take two sections, one here and one here, section 1 and 2, the velocity profiles will be different. The center line or the maximum velocity at 2 will be more than the maximum velocity at 1, and after this region we will have a parabolic velocity profile, and after this field region, at any cross section, be it this one A or B, it will be the same profile and the parabolic profile. So that is the thing when we call that the flow is now fully developed or hydrodynamically developed, okay. And we know that the solution of this velocity profile is W equal to, okay, W is the z component of velocity, that is equal to W max into 1 minus r by r whole square, or W max is equal to 2 into W average into 1 minus r by r whole square, where this W average is nothing but the total volume flow rate Q by the cross sectional area pi r square. And also you can find this Q by what? You can find this Q from the uniform velocity, and here the flow is uniform, right? So here it will be v into pi r square, right? The volume flow rate. So by this, now I mean we know this velocity profile. If you want me to solve it, just tell me in the video, then I can solve it in some later video. But now, because of the paucity of time, I will assume this velocity profile to be valid in the fully developed region. So this velocity profile is valid for the fully developed region, okay. And this flow is called the Hagen-Paisoli flow, okay, named after two famous scientists, Hagen and Paisoli. So fully developed flow profile, okay. So I will tell you that how can you solve it, or maybe rather I will take a small recap. So the Navier-Stokes equation, what does it say? I don't remember the form actually, so let me try to remember, try to recall the form. So if I write the z momentum equation, okay, in the cylindrical coordinate, okay, if I write that, then what will that be? Rho into del uz by del t plus uz into del uz del z plus ur del uz del r plus, so what was the divergence, I mean v dot del for the cylindrical coordinate that I have shown, I think, but I don't remember that. So I require this one, right? I require this one. So v dot del, okay. So u theta del uz del theta into r, and that will be equal to, minus del p del z plus mu into the second order terms, this plus, okay. So here will be the Laplacian of the velocity. So as far as I remember, it was something, this term, uh, r square, this one, plus 1 by r del qz del r, then plus this one, r square, right? I think this is correct. Let me see once the Laplacian terms. There is no glory to remember all these things, okay. You must know the mathematics. I mean, rather than remembering these expressions, you should be able to derive the cylindrical form from the Cartesian form. That will be more useful, okay. Yes, I am right. Obviously it is good and helpful if you can remember these things, but still there is no glory in remembering all these terms. So now fully developed flow means what? That at any axial position, at any z value, the u will not change, the uz will not change. That means duz equal to 0, and this is the fully developed flow, right? And now the flow is axisymmetric. So what do you mean by axisymmetric flow? Axisymmetric flow means that the del theta terms will be 0. Del theta of any parameter or of any fluid parameter, that will be 0, plus u theta equal to 0. That is no swirl flow, swirl velocity. So these two conditions together fulfill the term axisymmetric flow. Okay, and so u theta is 0, and also this is also 0, and we are considering the steady flow. Okay, so these conditions should be in your brain, that why I am neglecting these things. Okay, and here also in the similar way, this is 0 for FDF. I am not writing again that this is 0 for axisymmetric. And now let us see that if, so what is UR for fully developed flow. So that you can now refer to the continuity equations. So continuity equation, and continuity equation says for 2D incompressible flow, okay, incompressible steady flow, continuity equation boils down to divergence of the velocity vector, that is equal to 0. So what is divergence of the velocity vector? This, right, then this, another term is there, this, plus this is equal to 0. So for fully developed flow this is 0, right, FDF, fully developed flow, and we don't have any theta variation, that is because of the axisymmetric flow, right. That means that this term, so this term, how I can write it? I can write it, I think, 1 by r into r del uh, sorry 1 by r into del r of r into uz. Does it give me this term? Let's do the mathematics, or let me do it in the mind. That is 1 by r, and it is uz by r and r into, yes, it is giving it. So that means this is 0. Okay, so that means that r into this is equal to a constant. Okay, now at r equal to r, uz equal to 0, right, that means this constant is equal to 0, c equal to 0. That means sorry, I have done a tremendous silly mistake. So this will be ur. I hope that by this time you have already caught that mistake. So this all will be ur, because that was divergence. Sorry for that, that was divergence and not the Laplacian, right. And that means ur is equal to 0 for all the r's. Okay, so, and how I can write this? Because of the no penetration condition, right, and because of no slip uz is equal to 0 at the boundary. So that means u r equal to 0 in the fully developed region. So I can drop out this term, right, and also I can drop out which term, okay. So okay, now the after the simplification of the Navier-Stokes equation, the term will which sustained are this term, the axial pressure gradient, and mu into this term, right, mu into this term. So let me do it clearly, mu into this term, and this term you can write as 1 by r del r, right, into r into um, r into this thing, I guess, del uz del r. See that if it is coming or not, 1 by r into del square, yes, I think it is coming, right. uh, yes, okay, there is fine. So then the equation boils down to this thing, 1 by r del r r into del uz del r is equal to minus dp dz, and there was a mu, okay. So now this boils down to a very easy equation, okay, and actually this becomes ddr because uz is not a function of r, neither is it a function of theta, so it is only a function of r, okay. uz is only a function of r, it is not a function of z and not a function of theta, okay. So and now you can see that this is only a function of r, this is only a function of z, right. So that means that uh, it is only possible if both are constant. So your equation boils down to mu into 1 by r ddr r into del u duz dr is equal to a constant. This is a very easy equation and you can solve it with the boundary condition at r equal to r, uz equal to 0, that is because of the no slip, right, and at r equal to 0 because of the symmetry condition del uz del r equal to 0, okay. So these two conditions you do have and you can solve it, okay. So why symmetry condition? Now mathematically you can see that it is a circle, so intuitively it is okay, right, that here if I cut the domain with a plane, above the plane and below the plane everything is same, then the profile must be symmetric, okay. But this is a very intuitive and hand waving type of argument. There is a mathematical argument obviously, and we can show that the r equal to 0 is a singular point when we transform from xyz coordinate to the r theta z coordinate. So when we transform into that, r equal to 0 is a singular coordinate. But at that singular point, if the this kind of derivatives, okay, at the singular point, if it is a singular point, I mean, so how can you find this kind of derivatives? To have this kind of derivatives, right? But here, I mean, that is the problem. You see that in the Cartesian coordinate, you did not have anything like 1 by x, 1 by z, or 1 by y. But when we transformed from Cartesian coordinate to cylindrical coordinate, now we have something like 1 by r into del u z del r. So how can you calculate that? So you have to calculate that by limit r is tending to infinity 1 by r del u z del r. So then it becomes, I can write it del u z del r right, by r. So if del uz del r is 0, and which is the symmetry condition, if del uz del r at r equal to 0 is 0, and at r equal to 0 r will also uh, r will also go to 0, so then this is going to 0 and this is also going to 0. So then you can apply the L'Hopital rule and you can say that this is equal to this thing. Okay. So to have this term defined at r equal to 0, you must have this del u set del r equal to 0. Okay. So this is one of the condition. I mean, and this is called the regularity condition. Regularity condition. So it arises because of the singular point when we transform the Cartesian coordinate to the cylindrical coordinate. Okay, and this we also call the symmetry condition because it is applied at the line of symmetry. Okay, now it can also, I mean, be shown that the solution that is uz that will be a function of r. Okay, if you calculate the uz of minus r, okay, that will be same. So that can be shown from the differential equation. So from this differential equation, what you can do is you can substitute r tilde is equal to minus r. Okay. So then you see here we have another del r here, another del r here. So two del r are here and also two r's are here. So minus 1 will be cancelled out and that will be again plus 1. So there will be no minus 1. I mean, what I am meaning is that if I write this governing equation, so let me delete all these things. Okay. So this was r into ddr 1 by r. So if I have to write this equation in terms of r tilde, then how can I write? So r tilde is equal to minus r. So 1 by r will be 1 by minus r tilde, and that will be del r will be equal to del r tilde, another minus 1 will be there and that will be plus. So here we have a r, so here we will have a r tilde but with a minus. Again we have a ddr, so ddr r tilde will have another minus and that will make it plus, and this will be uz and that will be equal to constant. So you see, both in terms of r and r tilde you are having the same differential equation. So you put either r, you put either minus r. So, and also I want to tell you that here we do not have the concept of minus r. So that is also another tremendous mistake. But I just want to show you that from these two equations, if you just do a mathematical exercise, that is you are just putting instead of r minus r, then also the equation remains same. Okay. So if there something exists like here it is r and here it is minus r, it will be a symmetric profile. Okay. So without calculating the thing, you can already say that. Okay, without solving the whole profile you can finally say. But now you please don't have the concept that there exists some minus r. Minus r is not there. The domain is 0 to r. Okay, that is we have a pipe and it is 0 and it is r. Okay, so the domain is defined between 0 to r. So for r, so this is the domain. Okay, and if I exclude the boundary, then I can write this one. So why it is okay, now it is working. And for all theta. Okay, so theta being 0 to 360 and maybe some z equal to from 0 to L, okay, maybe some length, but there does not exist any minus r. Okay, r is only from 0 to r. R is always non-negative. It can be 0 but it is always non-negative, but mathematically I have just shown you the concept. Okay, so it arises fundamentally because of the singularity condition that we get when we transform the Cartesian coordinate to the cylindrical coordinate. But you can say from mathematically, if you replace the variable r with minus r, then also you are getting the same solution. Okay, but it is again I am saying that this is not the correct way. I mean the second way, it is better that you can forget it. Okay, so I mean mathematically it does make a sense, but it does make sense, but physically and also I think mathematically it also does not make any sense, because you have already defined that your domain is in Cartesian coordinate, your domain is like this. Okay, so this I showed earlier in my early lecture. So from this you are jumping to the domain this one. Okay, so it is better that you don't put the second concept into your mind, and I am sorry for that. That was valid if the domain was like this. Okay, then that argument was valid. But as you have already defined the domain in terms of mathematics also, then that second logic does not make any sense. Okay, but if you have something like, I mean a plate, okay, and you have the same boundary conditions here and here, maybe some heat flux or some temperature, then you define your x and y coordinate here and your origin here. So then you can say that if I now define a solution for this half domain, so this is the solution for the positive x. Now if I do the same solution, if I write the same differential equation in terms of minus x, then you will see that that you will end up with the same differential equation. So there this the second argument was valid, because here the domain is from minus L to L. Okay, so all these things I am telling because I always say that don't think like I am learning only this problem. You should think like I am learning a concept, and learning this concept can help me to solve hundreds of problems. Maybe you can solve any other problem in any other domain, because whatever I have told you, that is mathematics, that is applicable not only in the heat transfer but also in any other field. Okay, so this type of mentality should be there in your mind. Okay, okay, so now I think I have talked a lot about how to derive the Hagen-Poiseuille velocity profile. This I have done because I promised you that you don't have to see any other lecture or any other notes to see the logic behind every step. So I thought that I will skip this, but I I have already told you that how you can get this velocity profile. Okay, this one. So if any one of you have already forgotten this thing, or if you even you even if you haven't studied this, I think this will benefit you. But obviously I haven't gone to the deep fluid mechanics still. So now we know that the velocity profile is this in the fully developed flow. So the moment I go for the thermal analysis, so there can also be a thermal boundary layer. So let me again draw the plate, right? So there can also be a thermal boundary layer. So this is my plate. I am not drawing the circle. Okay, let me draw it. It will not take much time, right? Okay. Why this part always? I mean, this half is good, but why that half? Okay, now it looks good. So if the drawing does not look good, then I feel bad actually. So, and this is the center line. Okay. Now if the fluid is flowing with a temperature of, let us say, T infinity, and the plate is having a temperature T wall, okay, plate, the wall of the pipe, okay. Now this T wall we do not know, because I have already told that the flux, the boundary condition is uniform heat flux. That is, we have the Q wall is equal to constant, some constant. This is our boundary condition. So we do not know that how this T wall will vary. Okay. So there will be some development of the temperature boundary layer, right? Okay, so there will be some development of the temperature boundary layer, and also there will be some development of the hydrodynamic boundary layer. Now we have two options. The hydrodynamic boundary layer can develop like this, right? Or it can develop like this. Now you should be able to tell that in which case. So if this is the case 1 maybe, and this is the case 2. So in case 1 you can see that the hydrodynamic boundary layer, that is the delta by delta T is greater than 1, that means the nu by alpha is greater than 1, that means the Prandtl number is greater than 1. And for case 2, delta T by delta is less than 1, that means the Prandtl number less than 1. So sorry, delta by delta T is less than 1. So I have seen many students just mugging up that yes, for Prandtl number greater than 1, hydrodynamic boundary layer will develop slower, sorry, will develop faster, okay, and for Prandtl number less than 1, the hydrodynamic boundary layer will develop slower. I have seen students mugging up these things, but you don't need to mug up, right? If anyone in the interview asks this, then just draw the thing and you can know that for which case the Prandtl number is greater than 1 and less than 1. You can answer this thing just by seeing the drawing, okay. Okay, so here we can have 4 combinations, and which 4 combinations? So I am writing like this: hydrodynamically, hydrodynamically, and I am writing like this: thermally. Okay, so there can be 4 combinations. So one is hydrodynamically developed, thermally developed, okay, and another is okay. So I am writing this developed with the right sign. Okay, so let me write it with another color. So hydrodynamically developed, I will denote this with a tick mark, and thermally developing, okay. So developing I will denote by a cross. So another combination can be hydrodynamically developed, thermally developed. Another combination can be hydrodynamically developing but thermally developed, and both developing, right? So we don't have any analytical solution for this, we have to go for the numerical solution, okay. Now hydrodynamically not developed and thermally developed, I don't know that if there is an analytical solution for that, is not, so I have to study that, okay. I don't know, I think there is no, but for these two things, that is hydrodynamically developed and thermally developing, we have analytical solutions, and we will study these two, okay. So firstly we will see the most uh, simplified case, the simplest one, that is the hydrodynamically and thermally developed flow. So now our focus will be the sorry now our focus will be hydrodynamically and thermally developed forced flow. Okay, flow, not forced, flow with uniform heat flux condition. Okay, uniform heat flux condition. Okay, so very obvious, not obvious, but still here our assumptions will be the steady. All the assumptions those were valid during the derivation of the energy equations, that is the homogeneous isotropic fluid, all those things. So the additional assumptions are steady, axisymmetric, right? Steady axisymmetric flow. Okay. Okay, so we can take another assumption, that is constant property fluid. Constant property fluid. Okay, that is the fluid, that is the fluid properties are not changing with temperature. Okay, in practical applications you have to think about this assumption, because the properties like Cp, mu, this actually changes with temperature. Okay, so you have to think about these applications, about these assumptions in practical applications. So now let us formulate the problem. So in cylindrical system, the governing equation, so I will write the energy equation Cp form. Okay, so what will be that? Rho Cp del T of temperature plus U Z del Z, right, plus UR del R plus U theta del theta into 1 by R, and that is equal to nothing but alpha, not alpha because rho Cp is there, k into, and as k is not changing with position, it will be Laplacian of t. Laplacian of t will be this, plus 1 by R del R into R into del T del R, right? Again I am saying that there is no glory in remembering this. Okay, if it is a good institute and a good exam, then it should be provided either the form of the Laplacian or the governing equation. So this plus this one R square del theta square. Okay, and plus beta t total derivative of pressure and the viscous generation. Okay, so now if we take another assumption, that is the large Peclet number flow or high Peclet number flow. Okay, so for large Peclet number, and also if we take the, obviously the RE is high. Okay, so and it is enough if I say large RE flow, because thermal Peclet number is RE into Prandtl number. So even if the Prandtl number is small, if the RE is very large, then Peclet number must be large. So large RE flow and low Eckert number flow. So for large RE and low Eckert number, this thing can be neglected. Okay. that I have shown in my earlier lecture. And for constant property, this is 0. Okay, and it is hydrodynamically developed. So I am having this ur equal to 0. Okay, axisymmetric, that is why this is 0. So in your note you must write this like in this bracket or in your language, axisymmetric, and this is hydrodynamically fully developed flow. Okay, and then here also this is 0, sorry, here also this is 0. Okay, and this is 0 considering large RE plus small EC, and this is 0 because of constant property fluid. Okay, so that means the governing equation becomes, and obviously this is 0 because of steady. Okay, because this is steady. So now the governing equation becomes rho Cp uz del T del Z is equal to K into del square T del Z square plus 1 by R del R R del T del R, right? And if you take this rho Cp here, K by rho Cp is alpha. So I can write this alpha, right? So I hope that I am not doing any kind of silly mistake here. Okay, so if this is correct, and now for fully developed flow, we know that this uz is 2 into uz bar, right? Or if I can write it as w, so uz is w, I can write, so 2 into w average, right, into 1 minus r square by r square, right? So this I know the expression of uz. Okay, so now what you can do is just define, or let us do some order of magnitude analysis here also. Okay, so if I do some order of magnitude analysis here, so by now I think you should have been comfortable. If you have watched the previous discussion, you should have been comfortable with the order of magnitude analysis. So this uz is of the order of what? Okay, so let me write these things differently, the order of the each terms. Okay, so okay, what I will do is uz, okay, that is of the order of some uc, and that is of the order of u infinity maybe, that is the incoming velocity. Okay, or rather you should say that this is the maximum velocity, that is 2 into w average. This is the order of the uz. The z is of the order of some L characteristic length along the pipe. The T is of the order of some Tc that we don't know. Okay, we don't have. Okay, we have R. So R is of the order of R here. Okay, so now if we have this, then this term is of the order of 2 into W average into Tc by L. Correct? Okay. Now this term is of the order of, along with the alpha into Tc by L square, right? And this term is what? Alpha into Tc by, you see that this r and this r will be cancelled out, and here it will be r square. Okay. So again you see that here my heat flux is constant. Okay. So if my heat flux is constant, okay, so other than heat flux being constant, I can directly show you that if you consider, so it is a convection, so this is the convective term, this is the axial conduction term, and this is the radial conduction. So if you now uh, take a ratio of axial conduction by axial convection, then what will be that? Axial conduction is alpha Tc by L square, and convection is 2 into W average Tc by L, and that becomes again alpha by this thing, and this is 1 by Peclet number. So if Peclet number is large, then this is small, then this is much less than 1. So I have shown it earlier, but still I am showing it again. Okay. So that means for large Peclet number you can also neglect this term. Okay. For large Peclet number you can neglect this term. So this term I can neglect as to 0 for large P, if P is large. So axial conduction can be neglected. Okay. So now just think that fully developed velocity profile means what? Fully developed velocity profile means uz is not changing with z. Then if anyone asks you that what do you mean by fully developed thermal profile, or how can you define the thermally fully developed flow, then you should not answer that del T del Z is 0. So why you should not answer that? See, if del T del Z is 0, then what does that mean? That you are giving some heat, but the temperature of the fluid when it travels along the wall, I mean the pipe, it is not increasing. Is that possible? So that is not possible, right? If there is no other cooling facilities, then it is not possible that you are giving heat and the temperature is not increasing along the axial direction. That is not possible. So fully developed thermal profile does not mean that the T is not changing with Z. Okay. So now let us try to examine that. Then what does it mean when I say fully developed thermal? I mean thermally fully developed. So my next question is that what do we mean by thermally fully developed? I mean, we know that the thermal boundary layer will be merged, but mathematically, what do we mean? Thermally fully developed profile. So mathematically, what condition should be satisfied so that I can say this thing? Okay. So let us explore that. Okay. So let me write again the energy equation. Okay. And now in the energy equation, I can write okay, so now I will write the energy equation in some simplified form. So that is rho Cp, okay, del T plus U I del T del x or uj del T del xj. I think you are now comfortable with the index notations because we have worked hard with this thing during the derivation of energy equation. This is equal to the k into, okay, Laplacian term. So in Cartesian coordinate I can write it like this, okay, and plus the viscous dissipation phi plus beta t capital d dt of p, total derivative of p. I think I haven't missed any terms, right? Okay. So now let us try to write the each term in their order of magnitude. So this is something Tc by Tc. I will make this rho Cp here and make it alpha. Okay. So Tc by Tc, and this will be some UC Tc by Lc. I will tell you that what are those UC, TC, LC and small tc, and this will be of the order of alpha Tc by Lc square. Okay, and this will be something of the order of mu by rho Cp into some UC, the same UC by Lc square, and how it comes that I have shown earlier in the lecture video, that the in the previous discussion I have shown that how the order of magnitude of the viscous dissipation term is mu into UC by Lc whole square, and this is some beta by rho Cp Tc Pc by small tc, right? Okay. So we have seen that the temperature is changing with Z. Okay. So what can be other options that we can explore, that if those are changing or not, because we know that in hydrodynamically fully developed profile the velocity is not changing, right? So what can be some other option, let us try to find. So in thermal analysis, other than the temperature, which variable are very important? Heat flux is very important, also the Nusselt number, that is, okay, then the heat transfer coefficient, right, H, and also the Nusselt number, and here I will define the Nusselt number as H into d by k. D is the diameter of the pipe, okay, and I can write this H in terms of this heat flux by some characteristic temperature difference d into k, okay, and I can write this delta T is actually in terms of this characteristic temperature difference, okay, and here it is Tc, it is fine, okay. So now let me explore that if the H is changing or not, if the Nusselt number is changing or not. So my assumption is that my k is constant, okay, my k is constant. So if Nusselt number is constant, then my H is also constant. So now I know that Tc is not the thing, I mean the temperature is not the thing based on which I can, sorry, the, or I should say that the local temperature is not the thing, maybe the bulk temperature is the thing. So I will define the bulk mean temperature later, okay. But now we will, if we do the analysis, so I have defined the Nusselt number as q double prime by delta Tc into d by k, okay. So then this term becomes, in terms of the Nusselt number, what, q double prime, or if I say that, also I say that this is q double prime is h into delta Tc, right? So I can write this delta Tc as q double prime by h by Tc, and Tc, now I define Tc as my convective time scale, and I can define it by Lc by Uc, right? So this is Lc by Uc, and this is Uc by Lc into del T is q double prime by h. Okay, you see that these two terms are of the same order, that is q double prime by h into Uc by capital Lc. Okay, now let me put this thing into some another place. Okay, so this term becomes then alpha into q double prime by h into Lc square. Okay, okay, and these terms let us not touch now, because anyway we can neglect these terms, and if we even touch, then the order of magnitude is not changing. Okay, so by Tc by Tc. Okay, now what is this Lc? What do you think? So if I am considering the Nusselt number, so then inside the pipe my heat is propagating. So this is my pipe, my heat is propagating through this, and I am talking about the Nusselt number. Nusselt number here is concerned about the axial heat flow. Yes, yes, it is convection, and the flow is going through this direction, and it is carrying the heat in the axial direction. But this Nusselt number is defined based on the heat flux that is traveling in the r direction, that is qr. Okay, so that means here this Lc from the problem description, that must be the D. Okay, so if Lc is the D, then what do I get? So this is the Uc by D, and this becomes alpha into q dot by D square, right? Okay, now at the wall, at wall I can say that my heat that is going inside, okay, that is equal to k into del T del y by uh, sorry, k into del T del y at, so or actually del T del r, I am sorry, del T del r at r equal to r, right? So I applied this same thing in the external force convection also, but what did I get there? So in the external force convection, I am just comparing these things. External forced convection. Okay, this was what? Q was of the, so this was H into some delta Tc. Okay, so I could have write that H into some delta Tc is of the order of k into delta Tc by, so that was what, del T del y at y equal to 0, but that was, we were analyzing the the thermal boundary layer. So in the length scale we were writing this delta T, and we were writing that this thing H is of the order of k by delta t. So if I am now right, so I can write it like this. So then h d by k into, sorry, sorry. So then I can write, h d by k into delta t by d is of the order of 1. So then I can write, or there the Nusselt number was defined by not by L but by, no, not by D but by L. So nu of the order of L by delta t. So as L will vary, the delta t will also vary. I mean, there will be a functional relation between L and delta t, and that will be the dependence of the Nusselt number. But now for the internal force convection, so for thermally fully developed. Okay, so now let me proceed with thermally not developed. If the flow is thermally not developed, thermally developing, thermally developing flow. Okay, so in case of thermally developing flow, if I consider the same equation, that is the H delta T C is of the order of K into now del T del R. Okay, but here you see, if I draw the pipe for the thermally developed region, so if this is my thermal boundary layer growing, okay, so this is my thermal boundary layer growing. Okay, now this is the from this location, this is the thermally developed, this is the region which is thermally developed. But now if I focus on this region, okay, that is thermally developing, so then can you tell me that what should be the uh, length scale that I should focus on, because the effective temperature gradient is this T wall, and here I have something that is T infinity, maybe some T infinity 1 at section 1. So here the at this zone the temperature will not vary, that the temperature profile will be something like this if it is the heating case, right? So this is the T1, and the main temperature resistance I am getting is because of this layer, is because of this layer, that is the thermal boundary layer, and that is here the del T, right? So in the thermally developing region also I will get the same length scale, that is K into delta Tc by delta T, some delta T. This will not be not exactly be same analysis as of the external force convection maybe, but this will be we will see that this should be the same. Okay, I mean the analysis in the developing thermally developing region, we will do that. But here what my point is that in the thermally developing flow also the concerned length scale should not be D, should not be this one, that is D by 2 or D, because this R is not the length scale through which the whole heat transfer is happening. The heat transfer is happening only through this one intuitively. So this is the length scale is delta t, or let me call it as delta t dash, so that you don't confuse it with the external force convection. But then again here also I will not have my nu in terms of d constant. Okay, there also some variation will be there. So let me write it. So then I have this thing, this is of the order of 1. So h into d by k into delta t dash by d is of the order of 1. Then this is my nu is of the order of d by delta t dash. So you see that nu here is also not constant as you move along the z, because along the z this will grow, this delta t dash, then Nusselt number will also not be constant. Okay, Now if I now if I consider thermally developed one, so thermally developed flow. So now you see that thermally developed flow means what? You are in this region, right? You are in this region. That means now if you draw the temperature profile, then it will be something like this. Like, that is, the heat transfer is happening throughout the whole pipe. The heat transfer is happening throughout the whole pipe. Now the characteristic length here LC will be D, that I took here, D. So for the fully developed case, if I now write the boundary condition, that is H delta Tc is of the order of K delta Tc, now the LC will be D. So now it will be H D by K is of the order of 1. Okay. So for the thermally fully developed flow, Nusselt number of based on the diameter, that is of the order of 1, and Nusselt number will not change with the velocity profile. Okay, I have not told anywhere that this Q is constant or this T wall is constant. So for anything, be it a uniform heat flux condition, be it a temperature profile, I mean be it a uniform temperature condition, constant wall temperature condition, for both the cases the Nusselt number will be constant through, I mean along the Z. So that is the main mathematical description of a thermally developed flow. Okay, and if you see that if this is of the order of 1, then H is of the order of K by D, and K is also a constant and D is also a constant. So if K and D are constant, then H is also a constant. So H should be also constant. So this you should mind, this you should remember, that obviously there I will show you that there are other mathematical descriptions also in terms of the non-dimensionalized temperatures, but this is the fundamental definition, that is the Nusselt number will not change with Z. Okay, this you should keep in your mind. Okay, that we can show by the order of magnitude analysis. So I will stop the discussion here and we will go through the next discussion on the next day. I will solve that governing equation, but what I will tell you here, that now from this discussion you should learn that in any problem the choice of the proper length scale, when you will analyze the problem with order of magnitude analysis, so we have seen that the how powerful the order of magnitude analysis is, that you can avoid those hectic and tidy similarity solutions and you can get the uh, accurate variation of the dependent parameters just by doing the similarity solutions, sorry, just by doing the order of magnitude analysis. But in those order of magnitude analysis, the length scale, the choice of length scale, that is very important. Okay, so here just by the proper choice of length scale in the different regions, we can say that the feature of a thermally developed flow is the Nusselt number being constant or the heat transfer coefficient being constant if the K is constant. So with this I will stop today, and just tell me if you have any doubt, you can always post it in the comments. We will meet in the next discussion. Until then, goodbye, take care and thank you.